This is the first video about rational functions, but actually I want to spend this video talking about growth rates and shrinkage rates of functions in general, and they don't necessarily have to be rational functions. So let's say r of x is defined to be this function p of x divided by another function q of x. Now r of x will be rational if both p and q are polynomials, but there are lots of functions that are the quotient of two functions that aren't rational functions. So I want to stay a little more general than narrowing it down so much. Let's talk about some growth rates. So for example, let me draw our coordinate axes. What would happen to r of x as x gets really large? And so what we can do is we can use this notation as x goes to infinity. If p of x grows faster than q of x, right? So if the numerator is growing faster than the denominator, then our function will start going out and getting really, really big. R of x will approach infinity as x gets really, really large. Now this, of course, is the case where p of x divided by q of x is greater than 0. But if, for example, p of x is growing more faster but it's negative, then we could have the situation where our function grows down towards negative infinity. And that's another perfectly valid way to think about growth, is growing towards negative infinity or growing towards positive infinity are really two types of growth. Alright, so that's what happens if p of x is growing faster than q of x. Well, what if p of x grows more slowly than q of x? So I won't write it all out this time, but let's say that p of x grows more slowly than q of x as x goes to infinity, right? Well, in this case, r of x, whatever it does in this region, will eventually start approaching 0. That's because r of x, which again is p of x divided by q of x, if this denominator is getting big much more quickly than the numerator is, we're going to be dividing by larger and larger numbers, and so this ratio will be approaching 0. So if p of x grows more slowly than q of x, whether we approach from the top or from the bottom, we will be approaching 0 as x goes out towards infinity. The third possibility, which is in some ways a little more interesting, is if the numerator and the denominator grow at the exact same rate. So if p of x and q of x grow at the same rate, then, well, the true answer is, what happens to r of x? You need to do more work. And there are some techniques that you'll develop for rational functions that will allow you to precisely specify what number r of x approaches. I won't go into those techniques at the moment. However, if r of x does approach a number, a single number, then we call that number a horizontal asymptote. So let's say that r of x approaches this number here, and let's just pick, for example, let's say this is the value 5. Then this line, this dashed line, has an equation of y equals 5, and it's called a horizontal asymptote. And in that, you'll approach a horizontal asymptote if, for example, p of x and q of x grow at the same rate. And in fact, let's just look back real quick. In this second situation, where p of x grows more slowly than q of x, you also have a horizontal asymptote, which occurs right at y equals 0, and that's another horizontal asymptote. And just to be really thorough, if we go back to our very first case, where the numerator grows more quickly than the denominator, notice there is no single dashed line that my function approaches. It just keeps going up forever or down forever. So in this first case, there are no horizontal asymptotes. Alright, so that's what I'm talking about when I'm saying the growth rates of r of x as x gets really, really big. So now we've talked about what happens to our function as the numerator and the denominator grow. Let's talk about what happens when they shrink. So I'll draw in our coordinate axes. And let's label a point right here. Let's call that point A. And we want to know what happens to our function if, for example, the numerator approaches 0 as x approaches a. So if the numerator of our function goes towards 0 as the x values approach a, but also the denominator approaches 0 as x approaches a. Right? So what if both the numerator and the denominator approach 0? Well, just as before, there are three possibilities. The first one let's look at is, let's say that p of x goes to 0 more quickly than q of x goes to 0 as x approaches a. Well, in this case, in our first case here, r of x will also go to 0 as x approaches a, because the numerator is getting smaller more quickly than the denominator, so in general the whole function goes to 0. So as I approach a, let's say from the left, let's say our function is coming from underneath, but nevertheless r of x will approach 0. And from the right, well, maybe it's underneath, maybe it's above. I haven't really specified that, but what I do know for sure is that r of x is approaching 0 as x approaches a. Okay, well, there's another possibility. Our second possibility, let's suppose that p of x approaches 0 more slowly than q of x. In this case, let's think about what happens. So r of x, which is p of x over q of x, and the denominator is getting smaller more quickly than the numerator. So you're taking numbers and you're dividing them by smaller and smaller numbers. And so this whole thing should go to either positive or negative infinity, because you're dividing by small numbers, so the whole result is going to be really, really big. So let's take a look, and let's give ourselves another point to look at here. Let's look at the point B, and let's suppose that p of x goes to 0 more slowly than q of x as x goes to b. Well, then our function r of x should go towards infinity, and so maybe it does something like going down towards negative infinity there, and maybe from the other side it goes up towards positive infinity. Positive or negative, I haven't really specified, but you can bet that if the denominator is shrinking more quickly than the numerator, our function will be going either way up or way down. Alright, now what is this vertical dashed line called? This vertical dashed line is a vertical asymptote. And it occurs right at the point x equals b, right? So the equation of this line is x equals b, and that's the vertical asymptote. So there's one more possibility, just like before. What happens if p of x and q of x both shrink towards 0, and they do it at the exact same rate? So p of x goes to 0 at the same rate as q of x. And let's give ourselves a reference as, say, x goes to the point C. So let me just draw C right here. Okay, well, just as you might have thought, what this means is you need to do more work. Right? We know that r of x won't blow up towards infinity, and it probably won't go towards 0. It could go to any number in between. So let's just say, for example, that r of x will approach this number right here. Let's give that a number, a height of, say, -5. So that means r of x would be approaching some number right there at -5. Alright, and that's what happens if p of x and q of x go to 0 at the same rate. We don't know what number without doing more work, but we can be pretty sure it's not going to be positive or negative infinity. We can be pretty sure it's not going to be 0. So we just have to do some more work to find out what number it's approaching. Alright, so those are the three cases, and I want to make one more point. In each of these three cases, what do you think would happen at the point x equals a, or at the point x equals b, or at the point x equals c? Is there going to be a function value, or is there going to be no function value? Well, I'm going to argue in all three cases that x equals a, x equals b, and x equals c, our function, r of x, will be undefined. And that is because, for example, r of a is p of a over q of a, but p of a is 0, and q of a is 0, right? Our function, our numerator and denominator are going to 0. And 0 over 0 is undefined. You can't divide any number by 0. You can't even divide 0 by 0. So that means right at the point x equals a, there is no function value. And we just represent it by a hole in the graph. So a graph is nice and connected all the way up till we get to x equals a, and then there's a hole. And the same thing goes for x equals b. Right? R of b is p of b over q of b, which is still 0 over 0, which is undefined. In this case, we don't have to worry about where to put the hole. This vertical asymptote kind of takes the place of that hole. It represents that there is no function value there. And in the last case, r of c, well, again, that's still p of c over q of c, which is 0 over 0, which is undefined. And so we look at that number that our function's approaching, and right when we get to that number, we just put a hole in there to represent that there is no function value when x equals c.